what does it actually take for a giant steel bridge to literally rip itself apart in the wind? And how can just one line of bad code cause a multi-million-dollar rocket to just explode? Well, today we're going to open up a study guide on some pretty spectacular failures. We're going to see how these two disasters, one made of steel, one made of software, are absolutely essential lessons for anyone building our digital world today. So, how do we stop the software we build from collapsing just like a physical bridge? Well, the answer is all about understanding the patterns of failure. Because these two disasters, which are decades and whole disciplines apart, are tragically connected in almost the exact same way. Okay, look at this. A twisting bridge from 1940 and an exploding rocket from 1996. What could they possibly have in common? And, way more importantly, what can they teach us about the apps on our phones or maybe the code that you write every single day? It turns out, pretty much everything. All right, let's dive right in with our first case study, the Tacoma Narrows Bridge out in Washington State. Now, this thing was supposed to be a modern marvel of its time, but it only survived for 4 months before it just dramatically tore itself to pieces in a pretty normal 40-mile-per-hour wind. From the very moment it opened, there was a problem. The bridge deck would just rise and fall in the wind, which earned it the infamous nickname, Galloping Gertie. The design, yeah, it looked sleek and modern, but it was hiding this fatal, catastrophic instability. So how in the world did this happen? Well, it was a disastrous chain reaction. First up, you have the sail effect. See, the solid sides caught the wind like a sail on a boat. That wind then hit the deck, which was way too thin and flimsy, causing it to twist. And this created a terrifying feedback loop. The twist would catch more wind, which then caused an even bigger twist. But the real original sin here, the critical mistake, was that final step, the wrong test. They only tested it for weight, completely ignoring the immense power of the wind. Now let's jump forward 56 years to June 4th, 1996. This is the very first flight of the Ariane 5 rocket. And this time, the failure wasn't caused by wind hitting steel, but by just a few lines of code inside a massive multi-million-dollar machine. The entire disaster unfolded in less than a minute. Liftoff looks totally normal, but this new Ariane 5 rocket, it's much faster than the older Ariane 4. So at 36 seconds into the flight, a number, 1 representing its horizontal speed, simply gets too big for the little box of memory it was supposed to be stored in. It's a classic overflow error. Just 1 second later, that single error crashes both the main and the backup computers. The rocket, now basically without a brain, veers way off course and self-destructs. And this is where a bunch of small oversights just pile up into a total catastrophe. The fatal code, it was just copied and pasted from the slower Ariane 4 rocket. And get this, that piece of code was actually totally useless after liftoff, but they just left it running. Then, to make things even worse, engineers had actually turned off the error protection that could have caught this, all just to squeeze out a tiny bit of extra CPU speed. The final nail in the coffin? The backup system ran the exact same flawed software, a perfect single point of failure. And the result of that one preventable software bug? A $370 million firework display. I mean, this is the ultimate example of why just reusing code without retesting it for a new environment is a monumentally expensive mistake. Okay, so we've got a collapsed bridge and an exploded rocket. What is the connection here? This is where our study guide really comes together, as we look at the lessons we can learn from both physical and digital wreckage. And this is where it all just clicks into place. The specific bug was different, sure. One was aeroelastic flutter, the other was a 16-bit integer overflow. But look deeper. The root cause for both was a fundamental misunderstanding of the new environment they were in. The key oversight? Inadequate testing for those new conditions. It is the exact same mistake, just repeated 56 years later in a totally different field. This isn't just a coincidence, folks. It's a fundamental pattern of engineering failure. And this is why we have the discipline of software engineering. See, it's not just about writing code. It's this whole idea that we have to build software with the same rigor and foresight that a civil engineer uses to build a bridge, planning for every stress, every condition, every possible point of failure. The lesson from these disasters is that when we cut corners on that process, our digital bridges can, and they absolutely will, collapse. But technical skill and process, that's only half the battle. As our reliance on software just keeps growing, so does the ethical responsibility of the people who build it.
Professional integrity isn't optional, it's essential. This quote from the official Code of Ethics for Software Engineers really gets to the heart of it. Significant opportunities to do good or cause harm. That is not some abstract idea. The engineers on the Ariane 5 project caused $370 million in harm with this single oversight. The power to build our world comes with this profound duty to not break it.
So, how do we navigate this huge responsibility? Well, this code of ethics, it acts like a compass. The first point is public. Was it in the public interest to launch a rocket with untested code? Probably not. The second, client. Yeah, you have to serve them, but not blindly. Third, product. Both the bridge and the rocket clearly failed to meet high professional standards. And fourth, judgment. This one is huge. It's about having the integrity to be the person who says, stop, this isn't ready, we haven't tested it for these new conditions.
So we're left with this. The lessons from Galloping Gertie and Ariane 5, they're not just history. They are active warnings for us, right now. The next catastrophic failure is already in the making somewhere. The only question is, what part are you going to play in preventing it?